Hey guys, good to see you all again. So we are still in chapter 11 here, but as I'd mentioned previously, there are basically two really big topics that get introduced in chapter 11. It makes chapter 11 fairly tricky. The first one is rolling motion, which we've now discussed to some degree. And the second one is angular momentum, and I'd like to at least introduce this concept today. There's going to be at least two videos on angular momentum. My goal is to talk about angular momentum and how you calculate it in this video. And then our next video, we'll see like why we have it at all. Like why is it a useful tool? Why is it a useful model in physics? And that'll be the next video. So that's my goal. This is kind of tricky. I think it's really like not at all intuitive. It's not something that it's easy to wrap your mind around. So just be patient with yourself, be patient with me, and we'll try to get through it together. So the first thing I want to say about angular momentum is, like so many of these other rotational quantities that we've had over the last couple chapters, what we're going to do is take something we already knew about in a linear context and try to figure out what would be the analogous quantity for a system that isn't a linear system, but for a system that's spinning or rotating. So we did this, so we said, we had linear displacement and then we had angular displacement. We had linear speed and then we had angular speed. We had linear acceleration and then angular acceleration. We had mass and then we had moment of inertia. Trying to think of other ones. Oh, we had force and then we had torque, right? So we had all of these, we over and over and over again, we took our linear quantities that we had earlier in the year and came up with rotational analogs. This will be the last case of that, where we're going to take momentum, which we already knew about linear momentum in this course. Linear momentum, the momentum which is abbreviated with the letter P. And we said that the linear momentum is the idea that a moving object wants to keep moving. If you have an object moving at a constant speed, that's the linear momentum. And we noted that P is equal to the object's mass times its velocity. But now we're going to think about what the angular or rotational analog to that is. And to get a sense for that, we might just think about if you could imagine an object that's spinning. If you have any object that's spinning, it will, like an object moving in a straight line, the spinning object wants to keep spinning. So if I take a wheel and I spin it, that wheel wants to keep spinning and spinning and spinning and spinning. Eventually, of course, it will stop because friction is going to eventually, somewhere along the line, is going to reduce its angular momentum, but it has this tendency to want to keep spinning the way it's spinning. And that's one way of thinking about angular momentum. I want to start with maybe that very example. We're going to have, it turns out, two cases for angular momentum, two very different situations for angular momentum. The first case is what I just mentioned, this idea of, like, if you have an object, I could imagine maybe a turntable or a merry-go-round that's able to spin, maybe like so. Maybe it's got a certain omega here. Maybe it's spinning in this direction, spinning in the counterclockwise direction. So this thing is spinning, it wants to keep spinning. And so what I can do is I can define the angular momentum of this angular momentum, which we'll abbreviate as capital L in this case. I could say the tendency for this thing to want to keep spinning, the angular momentum L, is just going to be equal to, if we go back to this, our rotational version of mass and our rotational version of velocity. We're just going to use those two quantities that we've already established. So when we're in a rotational system rather than mass, I have moment of inertia, I. Okay, so this wheel, I'm imagining it might be a disk, is going to have a certain I, a certain moment of inertia. So instead of m, we have I, and then instead of v, of course, we have omega. That's our angular speed. Okay, so it's really very much analogous, and that's our expression for L, capital L. So this is a fairly simple, just kind of direct translation. One word I want to say about this, I'm going to say two things about this before we move on to case two. The first thing I want to note is something about the units. The units here are interesting. You might remember that I has units kilogram meter squared, and this is radians per second. Radians have no units. It's a ratio. So the unit here then is kilogram meters squared per second. The reason that's interesting is that that is different from our unit for linear momentum. This might not actually be that interesting, but it's important to note. Our unit up here was the kilogram meter per second. So here we have essentially, it's the kilogram meter per second. It's like linear momentum multiplied by distance again, which we saw over and over and over again when we were converting from one form to another. We multiplied by an r value, and that's essentially what we've done here. We have it's the same exact equation, or same exact units, just with one more m in the mix. The other thing I want to note about this is that this is a vector quantity. So I'm actually going to go ahead and I'm going to throw my little vector arrows in here. This is a vector quantity. And we haven't really talked about rotational vectors yet, and rotational vectors are a little bit weird. So your first instinct might be to think, okay, well, if the wheel is spinning counterclockwise, maybe that's the direction of the vector. That would be sensible. It turns out that's not the way it works. It turns out that the direction of the vector is actually going to be perpendicular to the plane of the rotating object. So in this case, if this is a top-down view of this turntable or merry-go-round, the direction of the vector is either going to be into the page. So into the page, we could think of that if this were like an XY plane, we could think of that as the Z direction. In fact, maybe let's do that. Maybe I'm just going to like randomly define this as existing in some XY plane like this. So if the platform is rotating in the XY plane, then the direction of the angular momentum has got to be in the Z direction. Now the question is it in the positive Z direction or the negative Z direction? And the answer, and the way we do this is we have to use something called the right-hand rule. And the way we use the right-hand rule in this case is you take your right hand. Obviously, it's important that we use the right hand. Maybe I'll zoom out so you can see my hand a little bit better. So I'm going to take my right hand, and I'm going to take the thumb of my right hand, I'm going to take the fingers of my right hand, and I'm going to curl my fingers in the direction that the turntable is spinning in. So I'm going to take my hand and I'm going to curl my fingers counterclockwise. So you can see my fingers are curled in the direction of omega. So I curl my fingers in the direction of omega, and then the direction of my thumb indicates the direction of the angular momentum vector. So in other words, in this case, what's the direction of my thumb? Well, it's out of the page. It's coming up out of the page, or what we would call the positive Z direction. I don't know, maybe I could quickly kind of write down that process. I could say curl fingers of right hand in the direction of omega, thumb points in the direction of the L vector. So that will be, that's the right, that's really small. I hope you can see that. Curl the fingers of your right hand in the direction of omega, and then your thumb will point in the direction of the L vector. If you need to pause and rewind and go look at that again, you can. You could convince yourself, by the way, that if omega were clockwise instead, then if I had to curl my fingers this way, my thumb would have to point down into the page or the negative Z direction. So that's a way of using this little weird formalism called the right-hand rule to figure out the direction of L. So that's case one. Let's take a look at case two. Case two is actually a little bit stranger. So maybe I'll try to do this up here. Case two. It's possible, and for right now, you're not going to have any idea why we want to do this, but you'll see maybe next video. It's possible to define the angular momentum for an object that's actually moving in a straight line. So for instance, I might have a little particle right here, and that little particle might have a mass m, and it might be moving up into the page with a velocity v. That's the direction of the velocity. So it has m and v. In other words, it would have a linear momentum. If we like, we could say it has a linear momentum mv. But even if this particle just keeps moving in a straight line, even if it just moves in this straight line and never, ever, ever starts to turn, I could still, if I wanted to, define the angular momentum relative to some other point. So let's say this point out here in space, I was going to call it point P, but maybe we shouldn't call that point P. Maybe we'll call this point, I don't know, this point right here. This is point B, whatever that means. We could define the particle relative to point B, and the way we do that is if I draw a vector, an R vector that's in the direction that locates this point, the particle relative to point B. In other words, like this. This now is a vector R. Okay? And so what I can say is, yeah, all right, great, we've got this linear momentum, but I could also define an angular momentum relative to this point simply by multiplying by R. Now, unfortunately, it's not quite that simple. So here we have an angular momentum, and I'm not going to use capital L, I'm going to use lowercase l. So we use this is a common formalism. We use capital L for something like a turntable that's a rigidly rotating object. But if it's just a particle moving in a straight line, we use lowercase l to define the angular momentum. And here the way I'm going to do this is I'm going to say that the angular momentum is the mass of the object multiplied by a cross product. And that cross product is R cross V. That's supposed to be cross. Sorry, not plus, cross V. I think with Mr. Walker, you guys didn't do all the details of the cross product, and that's fine. I'm going to sort of explain everything you need to know about what the cross product means. So if this concept of the cross product is confusing to you, don't worry. So here's what the cross product means. All it means for our purposes is the following. If I have R here, it turns out that when I do the multiplication of M, V, and R, the only component of R I'm interested in is the component of R here that is perpendicular to V. So this is R perpendicular to V. That's the component of R perpendicular to V. There'd be another component of R right down here. I'm not going to draw it, but you could imagine an arrow going down here, which would be the component of R that's actually parallel to V. We don't care about the parallel component, we only care about the perpendicular component. In dot products, if you remember back to like work, for instance, dot products we're interested in parallel components, and cross products we're interested in perpendicular components. So this was similar to torque. Torque is also a cross product. So what you might note here, if I imagine this particle moving in this straight line, as it moves in that line, the magnitude of R changes, right? As this thing moves, the magnitude of R is going to change as it moves from one location to another. R is going to vary in length as the particle moves up to here, and then to here, and then to here. R changes, but R perpendicular does not change. R perpendicular is constant. And so what I could say is the magnitude of L is just going to be M times R times V. That's the magnitude. Note the units are going to be the exact same. It's kilograms times meters per second, which is just kilogram meters squared per second, which is exactly what we had down here. So it's the exact same units. That's significant. So again, the cross product for our purposes, all that means for us is that we're interested in the perpendicular components. Once again, we can use a right-hand rule to determine the direction. It's a little bit trickier here. I have to do the right-hand rule between R and V. So what I'm going to do is I'm going to take the, I'll zoom out again. I'm going to take my right hand, and I'm going to point my fingers in the direction of R, which is actually going to be rather difficult to do. I have to rotate my whole body, I think. So I'm going to point my fingers in the direction of R. So R is pointing down and to the left, so I'm going to point my fingers down and to the left. And then what I want to do is imagine how would I move my fingers in order to get them to turn to curl into V, in other words, the direction of V. So my fingers are pointed in the direction of R, and then I want to rotate my hand such that it's going to turn into V, and the direction of V is up. So if I curl my fingers this way, so that now my fingers are up, I see my thumb is pointed into the page. So once again, in this case, the direction of the vector for angular momentum is going to be perpendicular to the page, as it was here. Here, though, in this other case, we had that the direction of the L vector was up out of the page. Here, I can convince myself with the right-hand rule that the direction of the vector is into the page. If that is hopelessly and utterly confusing to you, the right-hand rule, I mean, if this right-hand rule business was very, very confusing to you, I'm going to say don't fret. It's not something that you're technically responsible for in the AP, but I thought I'd mention it. You are, however, responsible for calculating magnitudes of angular momentum vectors for both the case of rigid rotating objects and for the case of particles moving in straight lines. That's all I want to say for now. Maybe some of this will make a little bit more sense actually in our next video when you see why we even bother to learn about angular momentum in physics. I'll see you then.